Math 1325, section 2.2 is what we're covering today. And we've got this right here, Math 1325 Fall 2022. Under assignments, I have the entire first unit ready now. So there are 7 homeworks, 2.1 through 2.5. Then 2 from chapter 3, 3.1 and 3.2. So these 7 homeworks. The review for test 1 is here. That's a major homework grade. Basically, a review is equal to all the homeworks of a unit. So if you got 100 on all 7 of these and didn't do the review, your average would be 50. Or if you got 100 on the review and didn't do any of these homeworks, your average would be 50. So the review average is basically 10% of your grade, and the homework average is 10% of your grade. And that way, in total, daily work is worth 20% of your grade. And then all 4 tests are worth 60% total, 15 each. The final's worth 20%. So the final's worth a little bit more than a regular test is. All 8 of these items are due on September 23rd at 11:59 p.m. There's going to be a 2-day testing window on September 22nd through September 23rd. And that test will appear right here below the review, but it won't show up until September 22nd. So once the 2-day window starts, then the test appears. You can open it at any point then, but don't open it till you're ready to start working on it. It has a 2-hour time limit. And if you open it just to see what's in there, your 2 hours starts counting at that point, and there's only 1 attempt per test. Homeworks and reviews can be done as much as you want until the deadline to get your grade as high as possible or to practice more. But the tests, it's a one-shot only situation. So let's go into section 2.2. Only 10 questions here. Okay, given the following graph, sketch by hand the graph of the function described, indicating how these 3 points labeled on the original graph have been translated. Okay, so this is another algebra concept. Translations, transformations, they sometimes call all of them. A translation is when you move points. So if you've taken an original function that's just some made up graph right here that has 3 key points they're worried about. If you were to do a negative outside of the function, negatives basically affect reflections. So there's a difference between a negative outside of a function versus a negative inside the function. For example, you could have y equals, and if you did the x squared parent function, say your parent function was x squared, which is a real basic graph in algebra where you have a parabola. If you did negative x squared like this, it would flip upside down. So a negative on the outside is a reflection over the x-axis. It flips from right side up to upside down. That's a vertical reflection. You're doing it in a vertical direction, up and down, vertical reflection, but you actually rotate over the x-axis. As opposed to having a negative inside of a parenthesis with x and then having it squared. That makes it a horizontal reflection. And you would flip it over the y-axis. And in this case, it wouldn't make a difference in the way the graph looks, but technically this right side up here, that would flip and go this way instead. And then the left side would flip over the y-axis and go to the right side. So sometimes if a graph is already symmetrical to something, like this one, this original graph is symmetrical to the y-axis. So if you reflect it over the y-axis, you don't notice a change at all. But it's also true that if you have a negative squared, that's the same thing as a positive. So that makes sense that it's the same as the original one. So that's the idea here, is that, whoops, I'm going to the wrong spot, cancel that. That's the idea here, that if you have a negative on the outside, not on the inside, that's a vertical reflection. So this distance right here, if you go straight to the x-axis, there's a distance of 3 right there. So that'll be repeated on this side of the x-axis, and you'll be right there at -1, -3. -1, -3, that's a spot on the new graph. Although that has it too, this doesn't have it, and this doesn't have it. So it's got to be A or C already just from that one point alone. If you're already on the x-axis and you're reflecting over the x-axis, you're not going to move. So 2, 0 should also be on the graph, and they both have that. So basically what's happening is you're changing the y values to the opposite. The opposite of 0 is still 0. The opposite of 3 is -3. And then you change this -5 and this coordinate to +5, or think about going 5 units back up to the x-axis right there, and then go another 5 this way. So that's why it's this graph right here, -3, 5. It's not 3, 5. Plus, this is a function. This passes the vertical line test. And if you're just reflecting it over the x-axis, it's still going to be a function. It still should pass the vertical line test. And this one doesn't pass the vertical. This wouldn't be a function anymore. So it couldn't be f y equals -f of x, because that's implying that it's a function already. So that's graph C. So that's what a negative outside of the function does, is it flips it over the x-axis. But here's one where the negative's on the inside of the parenthesis. So that affects horizontal directions. That makes all the x's change to the opposite. So this -4 right there is going to change to +4. And you'll have +4, but this -4 will stay the same. It needs to move 4 units this way to get back to the y-axis. Then you go another 4 after that. So the new point would land right here at 4, -4. That has 4, -4. This doesn't, and this doesn't. I already know the answer is C, and I only checked 1 point, but we should check the others to be sure. So now change this -3 to +3. The 5 will stay the same, or think about traveling 3 units this way to get back to the y-axis, then another 3 here. That's 3, 5. This has 3, 5. 3, 0. Now this time it will move because we're moving across the y-axis. So we're 3 units from the y-axis here. We need to go 3 units that way, or just change this x of 3 to a -3. So -3, 0. Yeah, this has all 3 points. So that was good how question 1 and question 2 showed both possible cases. If there's a negative inside the parenthesis with x, then it affects x's. If it's outside, then it affects the y's. And that's true with other types of transformations too. So other types of transformations, you can have adding and subtracting numbers, or multiplying and dividing. So we have this W-shaped graph. And then you have a multiplied to the x inside the parentheses. So that's a horizontal change. Now, if you're adding, subtracting, multiplying, or dividing inside of a parenthesis with x, not only is it horizontal, but it's done the opposite of the way it looks. So if a is some number between 0 and 1, like say a half, normally if you cut something in half, it makes it smaller. But with a horizontal change, it's going to do the opposite. Instead of a half, you get ×2. Instead of cutting it in half, you multiply by 2. So all x values get multiplied by 2. So if the original, now it's a little hard to tell here which one's the original. Okay. They should have done these in different colors maybe, because both of these are black, and they got this f of x, is that labeled here, but then which one isn't that? Oh, I guess it's not. Okay. So it's a little hard to follow this because of both of them being black, but the f of x on graph A is this one. And the f of ax is this one. But you only shift if you have adding and subtracting numbers. So this is not a shifting that's going on. That's why graph A is wrong. They're shifting this graph to the left a little bit. Everything on the original graph is moving to the left. That would happen if you had x plus some A value, because you would do the opposite of the way it looks. Instead of adding, you would subtract. This is a reflection upside down. So the original graph was here, and then the other one's upside down. That would happen if you had a negative on the outside of the function, if it was negative f of x. They may or may not be doing a reflection over the y-axis, but now this graph looks like it's to the left a little bit too, although now it's really hard to tell which one's which. And then this one's been shifted down. So we're not shifting to the left, we're not shifting down, or maybe it's shifting up actually. It's shifting up, and it's not a reflection. So kind of by process elimination, it must be C, but it would help if we had some points to work with here. Like say this point right here was 1, 0, and if A was a half, then you would multiply the x coordinate by 2, and it would move out to 2, 0. So that's what's kind of happening here, is that see how the farther the x is to the left, the farther this graph gets away from the original. But as x is smaller, then it actually gets closer. Where here, it's always the same distance away. It's always the same distance. That's a shift to the left. But if it's getting wider and wider and wider, it's a little hard to tell, but it's getting a little wider there. That's coming from a multiplying or dividing value. That's a horizontal stretching. So A is when you do a horizontal shift to the left. D is when you're vertically shifting up. B is a reflection upside down, a vertical reflection. And then C is a horizontal stretching. So anything that's bigger than 1 is going to go farther to the left and farther to the right. And then when it's less than 1, it actually gets closer in. But that one you could almost get it just by process elimination, by seeing that those other 3 graphs are definitely wrong. These ones are a little harder because they're not giving me any numbers to work with. But if you multiply the A outside of the parenthesis, then it's a vertical change, not a horizontal. And you do that one like it looks. So if A is between 0 and 1 again, that like a half, then you cut the y's in half. So that's a vertical shrinking. So it's not a reflection. Graph B is definitely out. You're not shifting upward. So it's definitely not B or D. Any y value would get cut closer down to the x-axis. So say like this spot right here at the bottom of f of x, say that's like -4. Well, if A was a half, then you would cut -4 in half, and it would be -2 where the new spot would be. So it's a vertical shrinking. It's getting in closer to the x-axis. Again, this one's just been shifted over to the left. That's just a reflection, or that's just a translation to the left. So this is graph C again. That's a vertical shrinking. So when A is between 0 and 1, you would think it would be a shrinking, and it is a shrinking on a vertical change, but on a horizontal change, it's actually a stretching. The horizontals, you always do them the opposite of the way they look. So similar deal here on number 5. We have y equals x plus 2 squared plus 4. So now we have the adding and subtracting numbers. This shifts the graph, like some of those choices had graphs that were shifted left or right. So the way I always remember it is, if the change is inside a grouping symbol like a parenthesis, or say a square root, or an absolute value bar, whenever the change is inside with x, then it affects x, and does so in the opposite way. And adding and subtracting are shifting left and right, multiplying and dividing are stretchings and shrinkings, and a negative is a reflection. So this has a plus 2 inside with x. That's a horizontal shift. Horizontal shift because it's a plus. but horizontals, you do them the opposite of the way they look. Normally +2, horizontally is to the right 2. This makes it go to the left 2. If it was x minus 2, then it would go right 2. This +4 is not in the parentheses, so it's not with x. Therefore, it affects y. So this one is a vertical shift. And those, you do them like they look, so that would go up 4. So you would take the original parent function. The parent function is y equals x squared. If you get rid of all the excess numbers, what's the most basic version of it? What's the most basic version of it? X squared is this U-shaped parabola. Then I take that and move left 2 and up 4. Left 2, up 4. And that's the new graph. And all we have is shifting going on here. There's no negatives to make it reflect, and there's no multiplying numbers to be stretchings or shrinkings. So really, it's all about, did it stay where it started? No, definitely not if there's changes to it. So does it go to the left only? Does it go right and up, or left and up? It goes left and up. It's definitely this graph D right here. And then, see, you could have, it could be, you probably won't get one this complicated, but you could literally have everything going on at once. There could be a negative that reflects it upside down. There could be, say, a 3 that's multiplied. So that would be a vertical stretching since it's outside the parenthesis, and then you do it like it looks. Then you could have, say, like an x minus 4 squared. And then, say, a +5. So I would have a vertical reflection. Vertical reflection over the x-axis. There would be a vertical stretching times 3. All the y's would get multiplied by 3. If the times 3 was here, then it would be a horizontal shrinking divided by 3, because you would do that the opposite of the way it looks. Then this -4 would be a horizontal shift. And you would do it the opposite of that looks. -4 is normally left 4, so that would make it go right 4. And then you would have a vertical shift. And that one you would do it like it looks, and you would go up 5. And a vertical stretching, if you go to the original parabola, one thing that helps sometimes when you get those is to put some points down. Parabolas go through 1, 1, and also -1, 1. And then they go through 2, 4, along with -2, 4. So this is the original parabola here. If you have a coordinate like 2, 4, a vertical stretch times 3 means you multiply the y values by 3. So that 2, 4 would change to 2, 12. And that's what ends up happening is it's really tall and thin, like so. That's what a vertical stretching does. And even the 1, 1, you would multiply the y coordinate by 3. That would give you 1, 3. So you'd be going through 1, 3 instead of 1, 1. And then you'd be going through 2, 12 instead of 2, 4. So it just pulls it up really fast. That's what the vertical stretch does. The vertical reflection, you would flip it upside down then. And then shift it right 4 and up 5. So right 4, up 5. And it would be a real thin upside down parabola over there somewhere. So that's how I handle these. I just take each part one by one, look for negatives that are multiplied in, either here or there. That would be reflections. Usually don't get negatives inside for parabolas, because if I reflect it over the y, it looks exactly the same. So that's more common to have the negative on the outside. The 3 could be here or there. You could have a vertical stretching or a horizontal shrinking. And then you often get these plus and minus amounts, either in one slot or both slots. Okay, so next is we're switching to this is a different concept here. Complete the square and determine the vertex for the following function. Since this is a polynomial with a highest exponent of a square, that's a parabola. This is a general equation of a parabola. The general equations are usually how you start off, but they're not easy to work with for their graphs anyway. The one advantage they have is you can see the y-intercept instantly, but it's hard to do much else with the parabola, the function, or the graph of it. So this is just the general form of a parabola. The general form is y equals ax squared plus bx plus c. And usually problems start that way. Now you want to turn it into what's called the vertex form, because then we can see the vertex of a parabola, which is the most special point of a parabola. It's the point where the parabola changes directions, the one time it changes directions in the whole graph. So one way to go from the general form to the vertex form, the only way to really do that is completing the square from algebra. Complete the square. And you can't complete the square unless you have a 1x squared. So it doesn't work with a negative 5x squared. So first snafu here is I have to factor out a negative 5 off this x squared part so that I can have a 1x squared here inside the parenthesis. And that's going to affect this negative 30x. That needs to be divided by negative 5 also. Negative 30 divided by negative 5 is positive 6. And then we put a plus blank for the completing the square process. When you learn completing the square in a college algebra class, usually the other side of the equation is 0, and you take this negative 43 and add it over to the other side and get it out of the way. And then you put a plus blank on both sides of the equation. We can't do that here because we have to leave this y here the whole time. We're not allowed to move anything over to that side. So I just put this negative 43 outside the parenthesis. It's kind of in the way. It's not the number I need to make me do this really well. So I just get it out of the way outside the parenthesis. And then for this plus blank, we're going to have another blank here. But unlike the ones where they're equal to 0 and you put a plus blank on each side, it's not automatically immediate what this is going to be. This is actually going to turn out to be the opposite of what I put here. So then you bring down the negative 5. Completing the square takes a trinomial like this. And it turns out when you factor it, you get the same factor both times. And that way you can write it once squared. So this always creates an x something squared. That's the whole point of doing it. And you can cheat a little bit by doing the answer first. It turns out somebody noticed that the answer always has half. Half of that middle number is what goes in the answer. Half of positive 6 is positive 3. And then literally like it looks, positive 3 squared is positive 9. And this is why we put plus blank here all the time, because we know it's going to be positive. Anything squared is positive. So you can't factor this. It doesn't factor. You could solve it with quadratic formula, but it doesn't factor. And quadratic formula is not going to help us here because we need this format. But if you had this trinomial, x squared plus 6x plus 9, if you were just given that back in high school math, and they said factor it, you would get 2 x's in the front. There's a plus here, so both answers are plus. We need 2 numbers that multiply to 9 and add up to 6. And coincidentally, maybe not coincidentally, they're both 3. That's the whole point of this, is we want the same factor times itself. 9 is the only number you can put here so that you not only does it factor, but you get exactly the same factor twice. So that's why you can write it once with a square. And that's why it's called completing the square. So you don't have to figure this out all the time. You can do that if you want, but it's just automatic. You can get it in a two-step process backwards. You take half of the middle number that goes in the answer, and then if you square it, then you find out the number that was supposed to be there. You would probably think, aren't we supposed to know this first before we get there? Normally you would, but this is a nice process where this always happens. Now, the only trick is I can't just add 9 to something because I want to. It's going to throw the equation out of balance. So we need to balance it with the opposite. And you might think, okay, plus 9, let's put a minus 9, because plus 9 and minus 9 are opposites of each other. But this really isn't a 9 right here. It just looks like a 9. This 9 is no more a 9 any more than this 6 is a 6. Because this negative of 5 affects everything in this parenthesis. There's actually a negative 5x squared right there. This negative 5 times 6, that's negative 30x. So if you want to know what do you fill in this blank, you have to multiply the negative 5 to the 9, multiply that out. That is negative 45. So then I need the opposite of that in the other blank. The opposite of negative 45 is positive 45. If I add and subtract 45 at the same time on the same side of the equation, I'm not changing the equation then. So this is a little trick of the trade, or a little bit of magic going on there, but it's plus 45 is what's going to balance everything. And then the negative 43 plus 45, those can be added together to make positive 2. So now I have the vertex form of a parabola, which takes the format a times x minus h squared plus k. And when you have that format, the vertex is easy. The vertex is the coordinate hk. And just like with transformations, you always do the opposite of the x value. Because really the format's got negative h. If negative h is positive 3, well then positive h would be negative 3. This is why those graphs, when you have this format, you always do the x the opposite of the way it looks. So instead of going right 3, you would actually go left 3. And then plus 2, that one's done normally. That's why you shift that one up 2. So this is like that example I made up. We're shifting up 2. We're going to the left 3. There's a vertical stretching of 5, and it's flipped upside down, a vertical reflection. All of that can be seen in the vertex form. You can't see that in the original format. Now the original format's got the y-intercept right here. That's the one advantage of it, but the vertex form is much better if you're solving things or graphing things. This is going to definitely be better. So I need negative 5 x plus 3 squared plus 2. That's the vertex form. And they have the y equals, in essence, s of x is the same thing as y equals. So negative 5 x plus 3 squared plus 2. Now the vertex is very easy. It's the opposite of the plus 3, negative 3, and then the 2 stays the same. And then that's all they're doing on this problem. But what could then be done is move to the left 3 and up 2. Left 3, up 2, that's the vertex. It's upside down because of the negative, and it's a vertical stretching times 5, so it's going to be really thin as it goes downward. That's a really thin upside down parabola. All of that can be seen from the vertex form. Just by seeing this, you can tell all that information. All of that's hard from this right here. Now the y-intercept is negative 43, so that would mean if you kept going down like this, it would eventually cross the y-axis, but it wouldn't happen until you were way down there at negative 43. We don't need that for this problem, but that's one thing you can tell right away. Okay, so now it also turns out, besides doing what we just did, there is a way to get the vertex alone from the general form if you don't want to do all that completing the square. if that's all you need. Now, if they ask you for the vertex form, you're forced to do the completing the square. But if you just want the vertex, there's actually a vertex formula. The opposite of b over 2a and f of that answer. And I'll first do it on problem 6 to show you that it works. So in problem 6, a was -5, b was -30, and c was -43. So we need to do the opposite of b. The opposite of -30 is +30. 2 times a, 2 times -5 is -10. And you work that all the way down till you have an answer for it. There's -3. Whoops. And then you do f of that answer for the y part. So apparently if I do f of or s of, whatever it is, if I were to do f of -3 into this function right here, it should equal 2 because I already know the answer is 2. So I'm assuming that works, but I can check it. -5, plug in -3, square it, -30 times -3, -43, and then when I press enter, it should say 2. Yep, 2. So you could do that. That's what we're going to do on number 7, actually. Number 7, y equals 3x squared plus 6x minus 18. So a is 3, b is 6. It turns out you don't even need c to find the vertex. It's the opposite of b over 2a and f of that answer. So get that answer first and then just plug it back into the original function. So opposite of b